Okay. Welcome to the Machine Learning with Python summary, what we've been covering over the week. Yeah. And we're just going to go through briefly whatever we have covered over the week. Yeah. Just an overview of what machine learning is, what it entails, and what the major aspects of machine learning are. Yeah, so in lesson one, we covered the basics of machine learning, and that is where we defined what machine learning is. And we said machine learning is a type of artificial intelligence that extracts patterns out of raw data by using an algorithm or method. And the main focus of machine learning is to allow computer systems learn from experience through without being explicitly programmed or through human intervention. Okay, that is the major thing about, or the major concept about machine learning. Machine learning is a subset of artificial intelligence, and it mainly focuses on allowing the computer systems learn from experience. And where is it getting the experience from? It's getting the experience from raw data that has been introduced to without being explicitly programmed or human intervention, or there being any human intervention. That is machine learning. Okay, so training a computer system to learn, or rather training a computer system from data, raw data that has been presented to it. So it's trying to get some conclusions or drawing some insights from that data through training it. Okay, that is machine learning. And machine learning can be applied in real life situations. For example, emotional analysis, sentiment analysis, error detection and prevention, weather forecasting and prediction, stock market analysis and forecasting, speech synthesis, speech recognition, customer segmentation, object recognition, fraud detection, and fraud prevention. Okay. Then after that, we covered the differences between machine learning and artificial intelligence. Yeah, and under machine learning, we covered the the major the major aspects of machine learning. We covered them. We covered also the artificial intelligence and where the difference comes in. And we said artificial intelligence focuses on creating intelligent machines. Okay, while machine learning focuses on training a computer system to gain experience from raw data such that a system can perform a certain task without human intervention. Okay, and we stipulated the differences. There are those differences or between machine learning and artificial intelligence. Now, we went ahead into the Python ecosystem, and under Python ecosystem, we talked about why Python is considered when it comes to data science. And the reason is it has extensive set of packages. Yeah, we have quite a number of packages that are usually inbuilt. Others need to be installed into your Python environment. But the thing is, Python has an extensive set of packages that are usually applicable in data science projects. Then we have easy prototyping, where we said Python, the reason, or this is another feature of Python that makes it the choice of language for data science, is the easy and fast prototyping. Okay, this feature is usually useful for developing a new algorithm. What is prototyping? Prototyping basically entails you're able, whatever procedure is used or followed in one algorithm is the same procedure that is followed in another algorithm. So it can be easy for you when you're developing a new algorithm. You're just going to follow the procedure, or you're going to use the structure that is usually used in other algorithms. The next feature is a collaboration feature, and Normally Python, when you're using Python, you can be able to integrate it with other machine learning, or not even machine learning, sorry. You can be able to integrate it with other softwares. For example, we talked about the Python with MySQL, yeah, and MySQL is a database. So in case your database has, I mean, your data set is in the database, the MySQL server database, then it would be easier for you to connect to the MySQL server, because Python has those provisions, yeah, of the collaboration, or rather the collaborative features, yeah, that you're able to integrate with other softwares. Then Python is one language for many domains. That is, when you look at the machine learning process, it's quite an extensive process. It has several steps that you're supposed to follow, and these steps are all performed in Python. Yeah, you do not have to go to another, for example, when you get to a certain stage of maybe the step for data preprocessing that you need to go to another platform, you can do it on Python. Yeah, so Python provides a platform where you're able to carry out quite a number of functions. All right. Then we went ahead into looking at the libraries used for data science. We covered NumPy, which represents numerical Python, and it contains the functions that can be used in mathematics, linear algebra, Fourier transformations, and so on and so forth. We have the pandas, and the pandas library usually helps in data manipulation, from the loading of your data to data preparation to data manipulation, to feature selections and selection, and so on and so forth. Then we have the scikit-learn, and the scikit-learn contains all the functionalities that are needed to perform, or rather that are needed in building of the algorithms, the machine learning algorithms. All right. Then we went ahead into looking at the machine learning models, and it entails the task, experience, and performance. Those are the major aspects of the machine learning model. There has to be a task that is being performed, and this task is being performed because the machine already has experience. Where does it get the experience from? From raw data, and it has to be there has to be the performance of that particular task. Okay, so there has to be a task that is being performed, and using an experience that was gained from the training process. Okay, then we went ahead into looking at the different machine learning methods. We have the supervised learning method, the unsupervised learning method, the semi-supervised learning, and the reinforcement method, and what each model, or rather what each method entails. Yeah. So under supervised learning method, um, this method or learning algorithm takes the data sample, that is the training data, and its associated output. So in supervised learning model, the the most unique thing with the supervised learning model, the data that you are using has labeled data. It has output features that, I mean, it has an output variable that you're trying to predict. The output variable is already there. Okay, unlike the unsupervised learning model, where you are given just data without output variable, and you're supposed to get patterns, or you're supposed to how you get insight from that method is through the patterns that are created by the data points that you have been given. Then under unsupervised, I mean the semi-supervised learning model, what happens is a combination of both the supervised and the unsupervised learning models. Then under reinforcement, um, under reinforcement in this kind of learning algorithm, there has to be an agent that we are trying to train over a period of time so that it can interact with a specific environment. Okay, that is the reinforcement. That was under lesson one. In lesson two, we covered the data collection, data loading for machine learning, understanding data with statistics, understanding data with visualizations, and the data preprocessing and what it entails. So we defined what data collection is, where we get our data from, and basically, under lesson two, we covered data collection. That is the process of gathering relevant data for machine learning. Yeah, where we get our data from. And in Python, we have not in Python, but when you want to do projects to do with data science, we have reliable sources of data. For example, we have the UCI repository, we have Kaggle datasets, we have GitHub, we have Google search engine. We also have Microsoft datasets and so on and so forth. There are quite a number. Then we went into how we are supposed to load in our data for machine learning. Um, so how to import and load the collected data into the machine learning environment. We covered that as well. We went ahead into understanding data with statistics, where we looked at, in case you want to view your data after loading in your data, you use the head function. If you want to check the dimensions, that is the rows and columns, you use the shape function. If you want to get each attribute data types, you use the .dtypes method. In case you want to get the statistical summary of your data, we use the describe function, yeah, which displays the count, mean, standard deviation, the minimum value, maximum value, the first quartile, the median, and the third quartile, yeah. So then if you want to review the class distribution, you want to check on the distribution how your data sets, or rather how your classes have been distributed. You use the .group by, then you specify the class, and you use the size function to get the size for each class. Then if you want to review the correlation between the attributes, correlation is basically the relationship between the attributes. We usually use the .core function. Yeah. Then we have reviewing the skewness, how your data has been distributed, how it is shaped. Yeah. So you use the skew function. Okay. That was understanding data with statistics. Then we went ahead into understanding data with visualization. And under this, we looked into univariate plots. And under univariate plots, we are trying to understand the attributes independently. Yeah, so we are going to be plotting. We want to understand how a particular attribute has been distributed. So under univariate plots, we looked at the histograms. And for you to be able to plot the histograms, of course, you have to use the matplotlib visualization library. Then from there, so you're going to use the hist function. And this is a count of the number of observations. The histogram, sorry, usually displays the count of the number of observations. Then we have the density plot. Under density plot, um, we have to specify the plot that we are plotting is the density. It also shows the distribution of the attributes. Then we had the box plots. This is univariate in nature and summarizes the distribution of each attribute. And it's going to show you the median, it's going to show you the maximum value, the minimum value, and also in case of an outlier, it's going to be displayed as well. That is under univariate plots. Then under multivariate plots, interaction and the concept behind multivariate plots, we are trying to check on the interaction among multiple variables. We have the correlation matrix plot, which shows which variable is having a high or low correlation in respect to another variable. In short, we are trying to check on the relationship between how different variables are correlated to each other. Then we have scatter matrix plot, which shows how much one variable is affected by another or the relationship between them with the help of dots in 2 dimensions. Okay, so that was just trying to understand your data, and that is usually exploratory data analysis, yeah, through statistics and also through visualizations. After that, we need to prepare our data. How do we go about the preparation? Data preparation, we have the first thing is data preprocessing, which is the procedure that makes our data set more appropriate for machine learning process. And data preprocessing techniques, we have scaling, and data rescaling make sure that the attributes are at the same scale. Okay, so generally attributes are rescaled into a range of between 0 and 1, and we can rescale the data with the help of the min-max scalar class of scikit-learn Python library. So that is the scaling. We have normalization, which is used to rescale each row of data to having a length of 1. And we usually use the normalizer class of the scikit-learn Python library. And under that, we have two techniques. We have the L1 normalization, which may be defined as the normalization technique that modifies the data set values in a way that in each row of the sum of the absolute values will always be up to 1. Then we have the L2 normalization. It may be defined as the normalization technique that defines the data set values in a way that in each row the number of squares will always be up to 1. So the difference is for L1 normalization, we are talking about the sum of absolute values, but for the L2, we are talking about the sum of squares. Okay? Then the third one is binarization, and as the name suggests, this technique modifies or this is the technique with the help of which we can make our data binary, and we can use a binary threshold for our data. For example, we already have for example, if you have a threshold value, so any value above the threshold value will be converted to 1, and the other value below the threshold value is converted to 0. Then we have standardization. This is the technique. This technique is useful in machine learning algorithm like linear regression, logistic regression, which assumes Gaussian distribution, that is normal distribution in input data set, and produces better results with rescaled data. So we can standardize the data, mean equals to 0 and standard deviation as 1, with the help of the standard scalar class of scikit-learn Python library. Yeah, so that is under data preprocessing. Then we go to data feature labeling. We have to label our data. Yeah, so most of the sklearn functions expect the data with the number labels rather than word labels. So therefore, we need to convert each labels into number labels. And this process is called label encoding. We are trying to convert the labels into number labels. Yeah. So, and we can perform label encoding of data with the help of the label encoder function of the scikit-learn Python library. Okay. Then that is data feature labeling. Then we have data feature selection. It may be defined as the process with the help of which we want to want to select those features in our data that are most relevant to the output or prediction variable in which we are interested in. So it is also called attribute selection. So we want to get, if you're given a data set and it has very many features, not all those features are relevant. So we have to select the most relevant features, and that is called data feature selection. So why do we need to have the feature selection? It reduces overfitting. It increases the accuracy of the machine learning model. Why? Because you'll be using the most relevant features. Yeah, so the accuracy is kinda certain. It reduces the training time. Yeah, because the lesser the features, the faster the training process. So the feature selection techniques, how do we select the features, the most important features? We have univariate selection, and under this, with the help of statistical testing, having the strongest relationship with the prediction variables. So we can implement a univariate feature selection technique with the help of the select k-best zero class of scikit-learn Python library. So in that case, we are trying to see which of the features have the best relationship, or they have the strongest relationship with the prediction variables. Then we have recursive feature elimination, and as the name suggests, the RFE feature selection technique removes the attributes recursively and builds the model with the remaining attributes. So we usually rank the features that we have in our data set based on their importance. So the less important feature is, you can be sure it will be the first one to be scrapped off, okay, until we remain with the most relevant features. Then you have the principal component analysis, the PCA, which generally, which is also known as data reduction technique. And it's a very useful feature selection technique because it uses linear algebra to transform the data set into a compressed form. And that is the concept behind machine learning. Yeah. So machine learning, in machine learning, you have to use PCA because you have to compress your data, yeah, into you have to reduce the data set to a point, to a compressed form that can now be used. Okay. So that was under data preparation. So how we go about how we go about loading in your data, pre-processing, I mean, preparing your data for analysis, and the most important concepts under that. Okay. So we went ahead to lesson 3, and under lesson 3, we covered classification algorithms, yeah, or rather supervised learning algorithms. And of course, we said supervised learning algorithms are divided into two. We have two categories: classification and regression. Yeah. So under classification, uh, under classification, uh, we looked at the full machine learning process, then the machine learning algorithms, and we looked at the full machine learning process, and we also looked at the machine learning algorithms and classifications, which are quite a number. Uh, the decision tree, we have the naive Bayes, logistic regression, support vector machine, then we had the random forest, then we had the regression, and under regression, we looked at linear regression. We said classification can be defined as the process of predicting class or category from observed values or given data points. So in classification, we have prediction of class or category. Okay. Then classification evaluation metrics, we have accuracy. Of course, you have to measure. Why do you need the evaluation metrics? We said once you build your model, you need to evaluate whether that particular model is performing in the right way, or rather, the performance is satisfactory for you to be able to go ahead with that particular algorithm that you built. Yeah. So we have the evaluation metrics, and under classification, we have the specific evaluation metrics, which include accuracy, we have the confusion matrix, we have the AUC or ROC, we have the precision, we have recall, and we have the F1 score. Yeah, those are the evaluation metrics. Okay. Then we went ahead into now looking at the various machine learning classification algorithms. And under the classification algorithms, which are under supervised learning, we had the logistic regression. And a logistic regression, say this is a supervised learning classification algorithm used to predict the probability of a target variable. So the nature of target or dependent variable is dichotomous, which means there would be only two possibilities. Yeah, remember this is a probability kind of uh, kind of a problem. So we want to predict the probability of a target variable, and the target variable is in form of a category. Okay, so then we enter ahead into the support vector machine, And under support vector machine, we say this is basically a representation of different classes in a hyperplane, in a hyperplane in a multidimensional space. So the hyperplane will be generated in an iterative manner by the SVM so that the error can be minimized. So the goal of SVM is to divide the data sets into classes to find a maximum marginal hyperplane. Then we have the decision tree, and under decision trees, they can be constructed by an algorithmic approach that can split the data set in different ways based on conditions. So in decision trees, we have conditions that are being satisfied. If it's not satisfied, we go to the other direction. Yeah. And the decision trees are the most powerful algorithms that fall under the category of supervised algorithm. Yeah. And they are kind of so accurate because the point is if a particular if a particular instance does not satisfy a given condition, then you do not go by it. Okay, so there has to be some satisfaction of conditions so that you're able to come up with the final decision. Okay, then we have naive bayes, and naive bayes classifier is a probabilistic machine learning model that is used for classification task. Yeah, and the crux of the classifier is based on the Bayes theorem, and in Bayesian classification, the main interest is to find the posterior probability, that is the probability of a label given some observed features. Yeah, so we are trying to predict an output variable based on the given independent features. Okay, then we have random forest, and random forest algorithm creates decision trees on data samples and then gets the prediction from each of them and finally select the best solutions by the means of voting. And under random forest is usually under ensemble models, and ensemble models is basically a combination of individual supervised learning models. Then from there, you get the average of the results of each model that you have, the combination of the models that you have. And in this case, random forests are as a result of a number of decision tree models. Then that was under classification. We went ahead into regression, and we said the key objective of regression-based task is to predict output labels or responses which are continuous numeric values for the given input data. So basically, regression models use the input data features, independent variables, and their corresponding continuous numeric output values, the dependent or outcome variables to learn specific association between input and corresponding output. Yeah. Then we have the regression evaluation metrics, and after that, sorry, under that, we have mean absolute error, which is the simplest error metric used in regression problems. It is basically the sum average of the absolute difference between the predicted and actual values. In simple words, the mean absolute error with the mean absolute error, we can get an idea of how wrong the predictions were. Okay. Then for mean square error, this is like the MAE, but the difference is that we are now dealing with the square of the differences of actual and predicted output values before summing them all instead of using the absolute value. Then we have R squared, and under R squared, this is generally used for explanatory purpose and provides an indication of the goodness of fit of a set of predicted output values to the actual output values. All right. So those are the regression performance metrics, and we went through the example that we have in the materials that we were using. Then we proceeded to lesson 4, and in lesson 4 we went through unsupervised learning. So what is unsupervised learning? It usually uses machine learning algorithms to analyze and cluster and label data sets. In unsupervised learning, please remember, we are dealing with unlabeled data sets. And these algorithms discover hidden patterns. So how does prediction um, occur in unsupervised learning methods. It occurs through hidden patterns or data groupings without need for human intervention. It is the ability to discover similarities and differences in information, making it the ideal solution for exploratory data analysis, cross-selling strategies, customer segmentation, and image recognition. So examples of unsupervised learning, we have clustering algorithms. And clustering is a machine learning technique that involves the grouping of data points. And given a set of data points, we can use clustering algorithm to classify each data point into a specific group. So data points that are in the same group should have similar properties or features, while data points in different groups should have highly dissimilar properties or features. So clustering, how do you come up with the clusters? Yeah, we have density based. Yeah, in these methods, the clusters are formed as the dense region. Hierarchical based, in these methods, the clusters are formed as a tree type structure based on the hierarchy. We have two categories under this. We have agglomerative, that is the bottom-up approach, where bottom-up approach, we begin with very many clusters where each data point represents a cluster. Then as we proceed, the clusters get reduced up to where k equals to 0. Yeah, then we use the dendrograms to divide the bigger cluster into now an appropriate number of clusters. Then we have the divisive, and divisive, we assume that the data is one cluster. Then as we proceed, we go ahead dividing the bigger cluster into smaller number of clusters. That is the top-down approach. Then we can partition, and under partitioning in these methods, the clusters are formed by portioning the objects into k clusters. Then we have the grid. In this method, the clusters are formed as a grid structure. So which are the performance metrics used in clustering algorithm? We have the Silhouette analysis, and under Silhouette analysis, we use it to check the quality of clustering model by measuring the distances between the clusters. And usually, the Silhouette score usually lies between +1 to -1, whereas +1 indicates the sample, how far the sample is from the neighboring cluster. Then we have 0. The 0 score, this is where the sample is on a very close or is very close to the decision boundary separating two neighboring clusters. Then we have when the score is -1, it indicates that the samples have been assigned to the wrong clusters. Then the second performance metrics, under that, we have the Davis-Baldwin index. And under this, the lesser the Davis-Baldwin index, the better the clustering model is. Then we have the Dan index. Usually, it considers the clusters that are close together, while DB index considers dispersion and separation of all clusters in clustering model. The Dan index increases as the performance increases, while the DB index gets better when the clusters are well spaced and dense. So where do we apply the clustering? Clustering can be applied in data summarization and compression, where we have the image compression. We can use it for collaborative systems and customer segmentation. It can also serve as a key intermediate step for other data mining tasks. It can be used for trend detection in dynamic data, can be used in social network analysis, and can be used in biological data analysis. So the types of clustering algorithms, we have the k-means, and under k-means, this clustering algorithm computes the centroids and iterates until we find its optimal centroid. Yeah. Then we have the mean shift algorithm. Under a mean shift algorithm, unlike the k-means clustering, it does not make any assumptions. In k-means algorithm, the assumption is that we already have a defined number of clusters. But when it comes to mean shift, we don't have to have the number of clusters defined. Yeah. So hence it is a non-parametric algorithm. So mean shift algorithm basically assigns the data points to the clusters iteratively by shifting points towards the highest density of data points. Okay, so that is mean shift. Then we have the hierarchical clustering. This is another unsupervised learning algorithm that is used to group together the unlabeled data points having similar characteristics. And we said um, we have two categories under hierarchical. Um, we have two categories under hierarchical clustering. We have the agglomerative hierarchical clustering, where each data point is treated as a single cluster, and then successfully merge or agglomerate the pairs of clusters. So the hierarchy of the clusters is represented as a dendrogram or a tree structure. Then under divisive hierarchical class algorithms, all the data points are treated as one big cluster, and the process of clustering involves dividing the one the one big cluster into various small clusters. Yeah. So that is the divisive hierarchical algorithm, which is known as the top-down approach. Then we went ahead into looking at the automatic workflows, and we say basically that is the the machine learning pipelines and what it entails, the challenges that you come across when you're dealing with the workflows. Yeah. And under the automatic workflows, it usually has to achieve successful execution and obtain reliable results. Machine learning models often requires standard workflows, and the workflow entails it has the components, different components. You have data ingestion. This step involves importing the data for use in the machine learning project, either in real time or batches from single or multiple systems. Then we have data preparation. We have to prepare our data. That is, after we import the data, it needs to be prepared for use in the machine learning model. Then we have the machine learning model training, where we train our model. Then we have to, that is where we build our classifier or the model, that particular model. Then we have model evaluation. So once the machine learning model is trained, it needs to be evaluated using the statistical methods and business rules. Then we have the machine model retraining. In case after you have evaluated your model, you're not satisfied with the performance, what you do, you have to retrain. Maybe after you have tuned your parameters or you have changed particular aspects in your data, then you can retrain your model. Then you have to deploy. After you retrain your model, which is not a compulsory stage because it depends on the performance of the model after the model evaluation. So the challenges associated with machine learning pipelines, we have quality of data. Remember, the quality of data provided heavily affects the success of the machine learning process. So inaccurate and reliable or incomplete data can lead to incorrect or unreliable outputs. Then we have data reliability. So ensuring the reliability and trustworthiness of data sources is another challenge. So you have to make sure that wherever you're getting your data from is a reliable source. Then we have data accessibility. So to maximize the effectiveness of a machine learning pipeline, data must be easily accessible. Okay. There are no restrictions to accessing your data. Yeah, so you have to make sure that data is easily accessible. So we say the major challenge with the machine learning pipelines or out the machine learning pipelines is data leakage, and data leakage can occur at the data pre-processing stage or at the feature selection stage. Okay, so you have to be careful during the data pre-processing. Make sure your data is standardized. Yeah, Then at the feature selection stage, make sure you at the feature extraction stage, make sure that you select, or rather you use the feature union function that will help curb the a problem that would come up, a data leakage problem that would come up. Okay. So the next thing is ensembles. We talked about the ensemble methods. Yeah, improving machine learning models, especially with the ensembles. And the ensemble models can enhance machine learning results by combining multiple models. And how do we combine the multiple models? It could be sequential, where in these methods the base learners are generated sequentially, one after another. Then we have parallel ensemble methods. In these methods, the base learners are generated in parallel, um, or they usually occur concurrently, simultaneously. Yeah. So those are the two ways, or the two categories of ensemble methods. And we have the example of ensemble methods. We have bagging, and under bagging, this aims to improve prediction accuracy and reduce model variance by aggregating predictions from individual models trained on randomly generated training samples. And under that, we have an example, which is random forests. A random forest is a bagging learning method. Then we have boosting, and under boosting involves incrementally building an ensemble model by training each base model estimator sequentially. Yeah. So remember, we said under ensemble methods, it could be sequential, it could be either sequential or parallel. Yeah. So for boosting, it's sequential. Yeah. So you build one model after another. Okay. Then we have voting, and in this ensemble method, multiple models of different types are constructed, and simple statistics such as mean or median are used to combine their predictions. Okay. Then we went ahead into looking at performance improvement in algorithm tuning, where we said algorithm tuning refers to the process of finding the optimal combination of parameters to improve the performance of a machine learning model. And the process is known as hyperparameter optimization. So, how do we go about the parameter tuning? We have grid searching parameter tuning. It systematically builds and evaluates the model for every possible combination of algorithm parameters specified in a grid. And this method exhaustively explores the parameter space defined in the grid. So it's going to go through every parameter that has been provided in the grid. Then we have random search parameter tuning, and under that, it involves sampling algorithm parameters from a random distribution for a fixed number of iterations. Yeah. And unlike the grid search parameter tuning, the random search parameter tuning explores the parameter space through random sampling. It doesn't go through every parameter. It does this random sampling. Yeah. And that is what you were supposed to cover under performance improvement. So that is basically what we covered in the machine learning with Python. And that was what was expected. Kindly make sure you go through the codes that are in the notes for better understanding of these particular concepts.